the seminar. Okay, so as I said, you are very welcome in this seminar, and please start.
Oh, thank you very much. My name is Masato Takita from Institute for Cosmic Research, the University of Tokyo. We are, I'm talking about, I will talk about the ALPACA project. This is an international project between Bolivian colleagues and Mexican colleagues and the Japanese colleagues. And thank you very much, Martin, for inviting me to this interesting and important ceremony of the 70th anniversary of the Chacaltaya Cosmic Ray Observatory. Oh, next page. No?
Yes, no, it's for us the pleasure to having you, dear Professor Masato. So you can start.
Yeah. Thank you. Oh, I am trying to. Oh, okay. First of all, happy birthday to the Chacaltaya Cosmic Ray Observatory. You are 70 years old now. Actually, our institute, the Institute for Cosmic Ray Research, will be our 70 years old next year. So you are 1 year ahead of us.
Yes.
So anyway, I would like to give a talk about the ALPACA experiment. ALPACA is the abbreviation of Andes Large Area Particle Detector for Cosmic Ray Physics and Astronomy, ALPACA. And this is a member of the ALPACA collaboration. You see, here are some members. See, Martin is here, for example. The total number of the collaborators now amount roughly to 50 colleagues. And as you know, the Chacaltaya, the ALPACA experiment, the experimental site is on the way to the Chacaltaya Cosmic Ray Laboratory. See, this is the UMSA Cosmic Ray Laboratory. And this is the ALPACA site. The main purpose of ALPACA is sub-PeV gamma ray astronomy in the southern sky for locating origin of cosmic rays by detecting cosmic sub-PeV gamma rays from cosmic ray accelerator in a galaxy, pebatrons. As you know, cosmic rays are accelerated in a galaxy, somewhere in a galaxy, but the origin we do not know. Since the discovery of cosmic rays back in 1912 by an Austrian physicist, Hess. Well, this is the energy spectrum of cosmic rays. The y-axis is multiplied by a factor of energy, e to 2.5. So if the cosmic ray energy spectrum is proportional to E minus 2.5, then the spectrum should be flat. So the energy spectrum is have a power shape with a power index roughly 2.7 before 4 PeV. And after 4 PeV, the spectrum becomes steeper, say minus 3.1. And this is called knee. You see, the shape is very similar to the human knee. That's why the cosmic physicists call its knee in the cosmic energy spectrum of cosmic rays. And this rapid decrease of the cosmic rays was discovered in 1958. And we believed, cosmic physicists believed that the cosmic rays below knee are of galactic origin and probably are above 10 to 18 electron volt. They are of extragalactic origin, and in between are, we don't know. There are many discussions about the origin, galactic or extragalactic, we don't know. So anyway, below knee, we believe that the cosmic rays are of galactic origin, and the most probable candidate so far is the supernova explosion. We think, or we believe so. And the supernova, I don't know. Anyway, the accelerator accelerates cosmic rays up to the PV energies. So, as an open question, did or do pevatrons really exist in our galaxy? Why? And why we observe sub-P gamma rays? Because cosmic ray accelerated up to several PeV, probably possibly by Perk wave acceleration mechanism at the SNR, and they interact with interstellar matter. But mostly they are composed of protons. And say cosmic ray and the intermatter stellar interaction produces neutral pion, pi zero, and the pi zero decay into 2 gamma. And the energy distribution of such gamma ray is represented in this big figure. Suppose the proton accelerator limit is 1 PeV, then the total gamma ray energy spectrum becomes like this. You know, minus 10 to minus 1 means 10% of the parent energy. So 1 PeV times 10%, 1.1 is 100 TeV, or 1.1 PeV. So sub-PeV region we expect from PeV cosmic rays. When cosmic ray interact with interstellar matter, producing pi node, and pi node decays into gamma. So we would like to observe such sub-PeV gamma rays to locate pevatron cosmic ray accelerator in our galaxy. One might think that the easiest way might be, why not observe a proton, cosmic ray proton? It's direct. Why do you observe sub-PeV gamma rays instead? The answer is very simple. You know, cosmic rays accelerated at the pevatron will be, the trajectory of the cosmic ray will be deflected by galactic magnetic field. So when they reach at the Earth, you know, they do not remember the original directional information due to the deflection by the galactic magnetic field. However, you know, if gamma ray is, if a cosmic ray interact near the, you know, this figure is a little bit confusing, but if this is very near to the source, interacting if a proton cosmic ray interact molecular cloud or anything, interstellar matter, near the source, then sub-P gamma ray is emitted. And the gamma ray goes straight, unaffected by galactic magnetic field. That means it remembers the parent cosmic ray accelerator direction. That's why we would like to detect sub-P gamma rays. Of course, another important method is the neutrinos, sub-P neutrinos that would be detected by ice cube experiment in the Antarctica. But in the galactic case, maybe the gamma ray detectors like us, for example, Tibet S gamma experiment may be 10 times more sensitive to ice cube experiment because they detect neutrinos which very weakly interacting with matter. So the event rate is very rare. Anyway, in the northern hemisphere, sub-P gamma ray observation started. First of all, the Tibet S gamma experiment observed sub-P gamma rays for the first time in the world from the Crab Nebula that when in 2019, some 3 years ago. And then Hawke experiment and the Russell experiment followed our experiment. And the three experiments have observed many sources, sub-P sources. And the Tibet AS gamma experiment also succeeded in the diffuse gamma ray emission along the galactic plane. This is the equatorial coordinate, and the galactic plane is in the thick black line. And this one is our field of view, out of field of view, the cosmic Tibet AS gamma experiment. So these blue points are sub-P gamma ray events along the galactic plane. So these guys, diffuse gamma rays are produced by cosmic rays interacting with the very diffuse interstellar matter spread over the whole our galaxy. So they are alone in energy and in direction. I mean, they don't point back to any sources, energetic sources. They are alone. Normally, if these gamma rays comes from a source, point source, anyway, accelerator source, then it might have, this energy spectrum is normally proportional to E to minus 3 or so. So if you observe one sub-P event, then you would observe 110 ETV events. But these are not accompanied by such events. They are alone in position and in energy. So it looks like they come from nowhere, along the galactic plane. That's why this is the first evidence of the sub-P cosmic ray of cosmic ray origin, proton origin. And this is the evidence. The event rate is consistent with the theoretical prediction. That's why this is the first evidence that the pepatrons exist in our galaxy. But so far, in the Northern Sky Survey, in spite of our efforts in 20 years, means in this case, cosmic ray field, cosmic ray physicists tried to find out pepatrons in the northern sky. However, until now, no compelling evidence of proton accelerator, cosmic ray accelerator, pevatron. But the Tibet diffuse result strongly suggests they must have, pevatron must exist in our galaxy. See, this gray region is the outside of the Tibet AS gamma experiment. And this region is in the field of view of the ALPACA experiment. This region includes galactic center, for example, very important, most promising pivotal candidate. So anyway, our ultra high energy experiment started by the Tibet AS gamma. By now, until now, a dozen of ultra high energy gamma ray sources were discovered by Tibet AS gamma Hawk and LASSO experiment in the northern sky. However, not comparing experiment is why in Bolivia. We need the experimental apparatus is very large, say 300 meter times 300 meter. We need such flat land at high altitude, more than 4,000 meters. Why so high? Because cosmic rays or gamma rays are absorbed in the atmosphere before reaching sea level. At sea level, there are many candidate places, but at high altitude and in the northern, in the southern hemisphere, Bolivia is one of the most promising candidate places. In Chile, probably they have some Atacama or something like that. But anyway, and the galactic center is observable in the southern hemisphere, which cannot be observed in the northern hemisphere. And the galactic center is the most promising candidate for the origin of cosmic rays. So we would like to observe some P gamma rays from the in the vicinity of the galactic plane, the galactic center. And this is the most important condition. Long-term collaboration between Bolivia and Japan. Good infrastructure, electricity, water, and road are all prepared. And since 1962, in the field of cosmic rays, for example, Basque's experiment is a Bolivia and Japan experiment. So we are friends for a long time. And this one is experiment outside of the ALPACA experiment. We called Chacaltaya plateau. And the ALPACA exposure time, how many hours we can see in a source, a certain source per year. Our air-shower experiment, the observation of this angle is normally 45 or 40 or 45 degrees. So if it is the cosmic ray, this angle is too low or zero. It's too horizontal. They traverse too much air, and that means cosmic rays or gamma rays will be absorbed by the thick air. That's why you can observe this angle smaller than some degrees. Some degree means in this case 45 degrees, or next case, in the case of 45 degrees, for the galactic center, the total observational time is say 2,200 hours per year. And if we take the zenith angle less than 6 degrees, so wider, then the observational time becomes much longer, say 3,000 hours. But if we extend the zenith angle from 45 degrees to 60 degrees, our energy resolution of the experimental apparatus becomes worse. So it's a trade-off. And this is the design of the ALPACA experiment. ALPACA experiment is composed of conventional air shower array of area 83,000 square meters. Each of this point means one square meter plastic scintillator. So we would like to use roughly 400 plastic scintillators. And these gray squares represent underground water trunk of muon detector. The total area may be 3,700 square meters, maybe total, adding up the 4 MD counters. Then the total area will be 700 square meters. The soil overburden is 2 meters. So the 2 meter underground, we will set up these counters. And each cell, the dimension is roughly 30 meter times 30 meter. And 16 small cells compose this structure. So each small square, gray square, is like this: 7 meter times 7 meter, 7 meter times 7 meter water pool. And 20-inch photomultiplier is like this, and water in. And when cosmic ray muon hits the water, it emits triangle light, and the 20-inch photomultiplier tube will detect the triangle light. And you see this figure, gamma rays, electromagnetic gamma rays, and electron plus positron components are absorbed in the thick soil. So only cosmic ray muons can punch through the soil and reach the water triangle detector. And on the contrary, the surface detectors, the conventional air shower array detectors detect mostly gamma rays and E plus and E minus. And by the surface detector, we estimate the energy and the direction of the parent particle. So the surface air shower array measures direction and energy of parent particle. And underground muon discriminate between gamma rays and cosmic rays, protons, and so on. Why? Because gamma ray induced air showers are electromagnetic air shower that contains only gamma ray and E plus ion, E minus. Then gamma ray induced air showers are all absorbed in the soil. So there will be no signal in the underground water triangle detector. This is a description of how we discriminate between cosmic ray, proton, and gamma ray by counting number of muons. You see, the cosmic ray induced shower contains these many muons, like this muons. And cosmic ray induced gamma ray contains essentially no muon. So very simple. For example, typically 100 TeV proton contains 50 muons, and 100 TeV gamma ray contains only 1 muon. So we can easily discriminate between gamma rays and protons. So if the underground muon detector records a signal, then it's cosmic ray. If no signal, then gamma ray. It's very simple. And we can separate gamma rays and the cosmic rays. For example, at 100 dB, we can reject 99.9% of cosmic rays while keeping gamma ray events 80% efficiency. So the reduction factor is 1,000. The cosmic ray reduction factor is 1,000. And this plot shows the sensitivity to point-like gamma ray sources. For example, the famous CT experiment, the sensitivity is here. This is a flux. This axis means flux. So the lower, the higher sensitivity. The lower, the higher sensitivity. Good sensitivity, better high sensitivity. So this 100 TeV is 10 to 14th. So energy electron. So above 100 TeV, ALPACA is better than CTA. Even for point-like gamma ray sources. But the Cherenkov telescope is narrow field of view, so they cannot observe, of course, diffuse gamma rays from the galactic plane. But ALPACA also can observe diffuse sub-PeV gamma rays. And there are many target sources in the southern sky. For example, galactic center. The Hess experiment, the Hess experiment in Africa observed galactic center in the vicinity of galactic center. And this one is the spectrum. As you see, 10 TeV, 100 TeV. And Hess experiment say observe 20, 30 TeV. But above 100 TeV, there is no signal. These are some theoretical extrapolation of the spectrum. So the ALPACA experiment can observe, if the sensitivity curve is lower than these flux expected value, then we can observe 5 sigma. This one is 5 sigma observation line per, in this case, 2 years, sorry. 4 sigma, in this case, 4 sigma, 2 years. But anyway, we can observe no problem. So this is most important and interesting result we would like to have. But soon we will get the result after ALPACA start operation. And Fermi bubbles. Fermi bubbles is like this from galactic center is here, and very energetic jet-like structure is seen. So very hot region. And we might expect something in this area. Nobody has ever measured the sub-PeV cosmic rays in this area. And for example, we can observe young SNRs, supernova remnants like this. This one is, there are many candidates. For example, famous SN1006, we probably can observe sub-PeV cosmic ray from this source. And RxJ 1713, this one is also detectable. This here 100 TeV. And Vera Junior RxJ 0852. This one is also observable. And there are many sources. For example, we can detect sub-P gamma rays from from nearby extragalactic source like Centaurus A. But this might be difficult because if the spectrum extends like this, then we can have chance. We will have chance to observe it. But if it is like this, probably not possible. We will see. And except for the sub-P gamma observation, we can do many physics, much physics. For example, cosmic ray anisotropy in TB region, and the sun's shadow in cosmic rays in the south, because the sun casts the shadow in cosmic rays because it has a finite size, 0.5 degree in diameter. And we can also study chemical composition of very high energy cosmic ray around the knee region. Well, we would like to let you know the current status of the ALPACA experiment. We think the ALPACA stage is like this. This year, we will complete the construction of ALPACITA, roughly 1/4 of the ALPACA. This part and this MD. And then this year to next year, we would like to make half ALPACA, half density. And the spacing is 21 meters. And then after that, we would like to make ALPACA a 15-meter spacing. So it's, the data starting, we expect the data taking will start in 2022, this year. And ALPACA is, ALPACITA is little ALPACA, as you know. And it is composed of roughly 100 surface plastic scintillation detectors and one MD pool. And the target, physics target, is a few bright sub-PeV sources and cosmic ray anisotropy. And this one is the underground muon detector design. And the UMSA guys, colleagues, did geological survey like this, and we found no problem for constructing this MD design. And this MD design is also made by the Bolivian company and Bolivian colleagues in cooperation with Japanese guys. And ALPACITA performance can be estimated by Monte Carlo simulation. ALPACITA will start data taking this year. So the performance is, we are very interested in the performance and say, look, this one is the ALPACITA sensitivity. Well, sub-PeV is here, 100. So, there are source energy spectrum observed by this experiment. The dotted line means no experimental point by Hess. So we just extrapolated. So the solid curve means the data point exists, but the dotted curve, no data point exists, just extrapolated. But anyway, we expect a few sources, 4 sources maybe by ALPACITA, 1 year, 5, 6. And then the next stage, half ALPACA, it is sensitive to galactic center, like this. The galactic center, the energy spectrum of the gamma rays near the galactic center is expected like this. And this is one half ALPACA sensitivity. And this one is ALPACA sensitivity. But Zenith angle is less than 60%. In this case, Zenith angle is less than 40%. So anyway, in any case, the galactic center will be detected by ALPACA. And this one is, this one is the summary of the ALPACA sensitivity. Maybe 7 sources about the infrastructure is, and the experimental apparatus is being made. And this one is a central electric circuit. And the perimeter, yes, fence, and the power line, and the cable drain, the light ring rods, long distance Wi-Fi, and water system. Water system has not been completed, but it's still under discussion, but we will soon make it. So this one is the picture showing the infrastructure, the fence and the cable drain, and so on, power line, and so on. And this is one of the latest pictures taken by the Bolivian colleagues, October 2021. Air conditioning systems are installed. And the Wi-Fi, we can monitor using web camera via network, and so on. So I would like to summarize my talk here. Sub-P gamma ray astronomy is crucial to identify the superparticle accelerator tevatrons. The recent successes by Tibet AS gamma experiment, followed by Hawke and Russell, opened the sub-PeV window in astronomy in the northern sky. However, there is no compelling evidence of the tevatron found in the northern sky. And meanwhile, the galactic sub-PeV diffuse gamma ray events detected by the Tibet AS gamma experiment strongly suggest, or it's evidence of that the tevatrons should exist in our galaxy. So, northern sky is over. So, new experiment in the southern hemisphere is desired. So there are many, many rich targets in the southern sky thanks to the Hess observation. And they did the experiment up to 10 TeV. So we, ALPACA experiment explored the southern sky for the first time with the technique established by the Tibet AS gamma experiment. And the 1/4 of the ALPACA experiment, ALPACA, will start operation this year. And ALPACA half density air shower array will start operation probably next year. And eventually it will be upgraded to ALPACA. So it's a very interesting phase. Therefore, por favor, apoye el proyecto ALPACA. Thank you very much. That's it.
Thank you very much, Professor Masato. So this was a very interesting talk, and now we are going to ask for the people for questions about the talk. Please, Ronald, if you have probably some questions by the chat in the G Suite session, please let me know. I have now in the Zoom session one question from one people. Yes, this is the question of Isabel Moreno. And the question is the following, Professor Masato. How clean or pure must be the water in the muon detectors?
That's a good question. We don't need very pure water, actually. In the case of super kamiokande, super kamiokande, I mean, in Japan, which is MEV gamma ray signal detector. In this case, we need a water purification system to mostly remove radioactive contamination in water. MEV background, MEV level radioactive background. But in our case, we observe muons. When muons traverse our water, say 1 meter, 1.5 meter, then it will deposit 200 MeV or so in water. So it's by far much energyless compared to the 1 MeV gamma rays in the background, radioactive background. So we don't have to need our water, pure water, in view of radioactivity. But we do need transparent water, of course. So pool quality, water pool, Olympic water pool, that's it. If you see, no problem.
Okay, thank you very much for the answer.
How to get, drinking water level is okay.
Okay.
At home.
Okay, thank you very much. So let's maybe start for a new questions. Also, you can please talk in order to make the questions, please, to Professor Masato. Ronald, I don't know if you have some question for the G Suite session.
Not yet, Martin.
Okay, please. Some questions.
Martin, I'm raising the hand.
Sorry, I didn't. Please go ahead. I don't know who's talking about, but go ahead, please.
Good morning, Professor Takita. My name is Fernando. Could you go, please, to slide 37?
37, I see. Wait a second, please. Second. So
yeah, this one. The previous one, please. Yeah, here. The 37 was okay.
37 is okay. So, sorry. Oh, it's okay. 37, sorry.
37, please. Okay, this one.
Yeah, I'm wondering why the sensitivity of alpaca, alpaquita, and alpaca half are different. Does the number of sensors affect the sensitivity of the project?
Yes. One is, one is the area is, surface area is proportional to the number of events we can detect. So alpaquita, alpaca will detect 4 times more gamma rays compared with than alpaquita. Alpaca observe 4 times more gamma ray, anyway, cosmic ray events than alpaquita. That's why. And mostly the area different, and it is not directly, in the analysis, the effective area is a little bit smaller than the covered area. We have to select the event inside of our surface area. That's why essentially the ratio of the area, surface area. And also muon rejector power is different because ALPACA has only one MD. Roughly 900 square meter MD, but ALPACA has 4 times more MD. That's why the muon cosmic ray rejection power is different.
Continue. In that case, if we increase the number of MD detectors, we will increase the sensitivity?
No, yes and no. In the law, if the gamma ray event is background free, it doesn't make any sense to increase the number of muon detector. But if it is background free, in the background free region, we don't have to increase the number of muon counters. But in the case of non-background free region, so there are many background dominant regions, it's very useful to increase the number of muon detectors, especially in the low. So as energy goes lower, these are non-background free region, dominant region, background dominant region, and this region is background free region. So the ratio is factor 4-5 and so on. It is proportional to surface area. In the first approximation. But in the case of this region, muon counter is much more effective to reduce these regions are not background free. That's why if you increase the number of muon detector, the sensitivity goes up. But we are not interested in that because in the low energy region, this experiment has a better sensitivity to Hertz. So it's not good to spend money in such direction. So in the case of background free case, we need to expand surface detector area to get more signal.
Thank you, Professor Takita.
Okay, thank you very much, Fernando, for your question. Any questions?
Martin, about the water quality, I have one more example.
Okay.
In the case of Tibet AS gamma experiment, I am engaged in the experiment also. And in the case of Tibet, we poured water, okay? Underground water, normal, from the well, and we put it, and of course, you remember, some material to put inside the water pool, to kill bacteria. You know the smell, floating in the pool. You can smell to kill bacteria. Underground water, chlorine.
Okay. Yes.
We put such material, and then the water quality or the muon peak, the water lifetime was 1,000 days. So after 1,000 days, the muon peak value becomes 1/E exponent. So roughly 30% of the original signal, but no problem. We could see 1 muon pulse.
Okay.
So typically water lifetime, transparency lifetime is 1,000 days. It's a quantitative answer.
Excellent, Professor Masato. Thank you very much. So I don't know if we have another question. So if not, I will thank you again, Professor Masato, for your very interesting talk, and we can end the seminar now.
Okay, no problem.
Thank you very much. and we are waiting for your visit at the end of this month.
Yeah. At the end of this month, I will visit.
Yes, so we're eager
you.
to having you here physically in our laboratory.
Yeah.
So thank you very much.
Thank you very much. Please enjoy your ceremony.
Yes, of course. Thank you very much, Professor Masato. Thank you very much
bye-bye.
for others.
Have a nice day.
Bye bye.